Formation of images by spherical mirrors. Very similar to lenses, spherical mirrors follow the same path. The flowchart for mirrors goes as follows. Its basis law is the law of reflection, and every mirror has its characteristics. It has a focal length, an object distance s, and image distance s prime. Image formation is done by ray diagrams. There's the mirror equation, which has the exact same shape as the thin lens equation, and the magnification equation, which is exactly the same. An image is formed when rays cross. So the big difference between lenses and mirrors is the ray diagram. For establishing ray diagrams, we need to go over the definitions of a mirror and its characteristics. Overview of mirrors. We have the mirror characteristics, image characteristics, ray diagrams, and the mirror and magnification equations. Now, we already know how to solve two of these. We understand what the image characteristics are, and we know how to deal with the mirror and magnification equations. So the two main things are the mirror characteristics and the ray diagrams. Let's go look at those. Mirror characteristics. The most common type of curved mirror is a spherical mirror. A spherical mirror has the shape of a section from a surface of a sphere. If I polish the inside of a sphere like this, then that's called a concave mirror. So the side that's polished is called a concave or converging mirror, or this is the back of the mirror where no light can get back there. If the outside surface is polished, this is called a convex or diverging mirror. Or once again, the back of the mirror is typically aluminum so that no light can actually get there. Every mirror has a center of curvature point and it has a focal point. Let's draw these in for a converging and diverging mirror. If I have a converging mirror, its radius of curvature is related to here. The radius of curvature for the spherical mirror is essentially the radius from here, the distance from the point C to the mirror as it goes all the way around. Now, if ray starts from infinity and reflect off the mirror, here's what we're going to see. The rays that cross after reflecting from the mirror is called the focal point. The focal length of this mirror is related to the radius of curvature. The focal length for a converging lens or concave mirror is 1/2 r, where r is the radius of the curvature. The concave mirror is very similar to the converging lens, and with the converging lens we had a single line representing the lens. The same thing will happen for a converging mirror. Instead of drawing a curved mirror, as this one on the left shows, I can draw the equivalent straight mirror where these little ends here indicate that it's a concave mirror, and this is a lot easier to deal with than this guy. So from now on, this is what a converging mirror looks like. Now we want to repeat this process for a diverging or convex mirror. Parallel rays come in along the central axis. This type of mirror will diverge the light away, but it appears as if the light is originating from behind the mirror. This is called a negative focal point. So the equivalent diverging mirror is the straight line, where these bent ends here imply a diverging mirror, and the focal length here is negative just as it is here, and then the last thing that we can write then is the focal length. The diverging focal length is -1/2 times r, where r is the radius of the curvature. Since mirrors and lenses have the exact same image characteristics, they have the same main equation, the mirror equation and the thin lens equation, they have the same magnification equation. I will not go through these. Let's look at the sign conventions. With all light, they start off from the left, going to the right. Here I have a mirror. It's either a concave or a divergent mirror. So then I have to talk about images formed on the left versus images formed on the right. Since light reflects off of mirrors, there should be no light in the back of the mirror. So therefore, any image that's formed by this smear on the left is going to be real, and if it's real, it's inverted, and it could be either smaller, same size, or larger. Therefore, the left side is the positive side. So if the image is on the same side as the object, you form real inverted images. On the other hand, if the back of the mirror, where there's not supposed to be any light, if there appears that there's an image that's formed, it must be virtual. Therefore, that image has to be erect and smaller, and therefore this side of the mirror is now negative. We now will go through the ray diagrams for converging lenses. There are 3 types of rays, but I will only consider 2 rays. The same ones that I did for lenses. Ray number 1, a ray parallel to the central axis, reflects off the mirror and goes through the focal point. Ray number 2, a ray that reflects at the middle of the mirror. There are 5 locations of the object to consider. Object outside of 2F, object at 2F, object in between 2F and F, and finally object inside of the focal point here. Let's draw the 2 ray diagrams. Number 1 goes parallel to the axis and now reflects through the focal point. Ray number 2 reflects from the middle of the lens. To get this reflection, imagine the image of the object reversed. You can see this image is in blue. Now draw the ray from the tip of the orange to the middle, and then from the middle to the tip of the blue. Where the rays cross, that's where the image is formed. You see that the pink image is inverted, real, because it's where the light is being reflected, and smaller. Let's go to the next one. Ray number 1 goes parallel, reflects through the focal point. Here's ray number 2. Putting a blue dot here to indicate where I'm going to reflect the ray to. Ray 2 then goes from the tip of the orange to the tip of the blue, and you could see here where they cross here with my pink image. That's an inverted, real, same size image. Let's go to the next 2. The object is inside F and 2F. We could see that ray 1 and 2 cross outside of 2F. In other words, you get an inverted, real, larger image. For my discussion with lenses, if an object is inside the focal point, I'm going to get a virtual image. So let's play with this a little bit to be sure that you understand. So I follow the ray 1, parallel, now it's going to go through the focal point, and then I follow the rays backwards. As ray goes through the focal point, I now draw a dashed line extending the ray. Now let's look at ray number 2. Now I look at the height of the orange and I put a little blue dot to indicate that I need the inverse of this image. So that's where it's got to reflect to. Let's go do that. So as ray number 2 comes in and reflects and we follow the rays back, you can see they cross behind the mirror. This image is erect. It's virtual. Why is it virtual? Because it's behind the mirror. There is no light back here. But yet our eye detects that there's light there. And this image is larger. We want to draw a ray diagram that summarizes all of the rays for a converging mirror. Ray number 1 never changes. Let's draw that guy in. The only diagram that changes is ray 2. So let's draw for each of them. For outside of 2F, we could see that the rays cross between 2F and F. When the object is between 2F and F, we see that its image is outside of 2F. Now for the virtual image. So when I'm inside the focal point, you could see here that the image is on the back side. So as the object moves towards the mirror, the image is inside F and 2F, and when the object is inside of 2F and F, the image is outside of 2F, and if I get closer and closer to the focal point, that green image will go to infinity, and then as it crosses the threshold across the focal point, the image appears to be coming from infinity towards the mirror. Very similar to a converging lens. Let's use Duffy's mirror applet to go through the converging mirror. So what you're seeing here is that I have a converging mirror. Again, look how the tips here point inwards, showing that it's converging. And what you find here is that this is the horizontal position of the object, this is the object height, and this is the focal length. Now, I have F and 2F here, and what you're going to see here is that the object is in red, and in blue here I have my image. So if the object is outside of 2F, the image is going to be smaller, but you could see that opposed to lenses, the image is going to be real if it's on the same side as the object, which is just the opposite of a lens. So as I move the object towards the lens, you could see that the image is slowly moving out, and when I get to 2F, or about, you see that they're roughly the same height. And then as it continues to go inwards inside of F and 2F, you could see that the image is larger here compared to the object. So as it continues to go out, it then goes towards infinity. When is it at infinity? At the focal point. And at the focal point, if I can get it there, you see that the rays are parallel. Remember the railroad track analogy that I used. So now the image is focused at infinity. As I cross that singularity point at the focal point here, the image goes from positive infinity to negative infinity. And what you're seeing here, oops, wrong one. What you're seeing here is that you could see that the rays on the back of the mirror are converging. But of course this can't be a real image because there's no light behind the mirror. So as I continue to move closer and closer to the mirror, you could see that this image is going to be larger, erect, and virtual. This is very analogous to a converging lens. The difference is the converging lens has it on the other side of the lens of the object, whereas for a mirror, the image is on the same side as the object when it's real